Hello, everybody. Welcome to API World 2019. And please welcome Rakesh.
Hi everyone, so this is Rakesh. I work as an analyst at Jade Global here in San Jose. And today, we'll talk about OpenCV, how to get started with deep learning and computer vision path. Turn on your mic. Hello. So, what is deep learning? Deep learning is nothing but an AI function that imitates how the human brain works and how we create a pattern using the data to make a decision in the particular problem or when we solve a problem. So it is basically a subset of machine learning, and what it uses is like a hierarchical model, which is called layers, to implement the underlying functionality. And what it's going to learn is when you input a data. So how different is it from machine learning? It's nothing but in machine learning you need to provide a structured data to get what you need. But in deep learning you provide unstructured data and get you can extract a feature from the particular data which is unstructured. And so here it implements something called deep neural networks in order to perform the processes of your particular problem. So how does deep learning work? So as I said earlier, it has something called hidden layers within this particular architecture to perform what you need. And so this layered architecture is nothing but neural networks. So neural networks, you could have heard the deep neural networks, which is nothing but as number of layers increases, the deeper it goes. So how it works, we'll just see in the next slide. And so this is nothing but a technique of classifying the information through layered approach. And so this, for this particular architecture, you'll have specific input sets where you provide or feed the data in. So this is what I told you about the hidden layers. So in this input layer, you have certain features. So every spherical object represents a feature. So you provide a feature set to the input layer, and then you perform mix and matches in the hidden layers. And then in the end, you get an output layer as the feature. So all the spherical aspects you see there is features. So everything happens in between the hidden layers is what is the deep learning is all about. So within this deep learning, you perform you can increase the number of layers to have a deeper model architecture, or you can decrease the hidden layers to provide a simple deep learning approach. So that's what hidden layers is all about. Computer vision. So what is a computer vision? So let's say you see this image or a slide and you understand this slide is about computer vision. But if you feed the same image to a computer, the computer will just see an image and that's it. So how do you make a computer learn from this particular image is what computer vision is all about. So as you can see, it is a scientific field which deals how the computers can gain higher level understanding from the image. And from perspective engineering, it seeks to automate this task. Okay, so you have a set of images. So how do you automate this task of learning from the images from all the data set which you currently have? So that's what computer vision is all about. So when you want to start with computer vision, what would be the first step? The first step would be acquisition of the data. So this particular data can be an image or a video or an image from Facebook, or you can crawl through the web to get these images or videos. So once the image is obtained, you should start with training. So what training is nothing but you feed in this labeled images to a model. And this model will start to get, so let's say you feed in an image of a cat and provide a label that it's a cat. And then you feed in an image of another cat and provide the label that it's a cat. So that's how you train the model. By the end of this training, that's what processing is all about. So the model will process and it will learn from the data, and by the end of the training, the model will understand that when you feed in an image of a cat, it should say it's a cat. and if you feed in a different image, it should say that that is not a cat. So that's how the computer vision architecture would feature, and that's how you provide to train a particular model. OpenCV. So OpenCV is what our upcoming demo is all about, and how to use this OpenCV to implement or to solve your AI problem. So OpenCV is nothing but an open source computer vision library. So this particular library has a framework of all the models or all the functionalities that you need as an AI or machine learning developer. So this OpenCV was built with computer vision in mind, and how to easily implement computer vision for a beginners or for an enthusiast who wants to get into this field of deep learning or computer vision. So it was founded in the year 1999 by Intel, and this is currently used in a lot of research purposes, and currently it has a version 3, which is which has pre-trained models in it, which you can implement to work on your AI problem. And so it is currently supported by BSD license. So BSD license is an open source license, and you can use this particular framework without any restriction of usage or modification. And this is also supports Mac and Windows. It's basically built on C++, but it also supports Python, Java, and other languages, whatnot. So OpenCV has more than 500 functionalities. So some of the basic functionalities that computer vision enthusiasts or ML enthusiasts would need are follows. Image processing. So if you want to work on an image, you want to create an image, or you want to display an image, you can use this framework. Or segmentation. So segmentation is something that we'll talk about in an upcoming demo. So let's say you have a collection of images, and that is a series of data. So how do you separate the image based on a particular value? So that's called thresholding. You set a threshold, you set a value for the image, and then you segment the data based on the value. And then comes transformation. So people who have worked with image editing or stuff like that would know transformation. It's nothing but skewing or warping or increasing the size, decreasing the size, stuff like that. Machine learning. So it also has, like I said, pre-trained models in it, like how implementation of Bayes theorem, or like the k-nearest algorithm, or the SVM support vector machines in it, and geometric descriptors. So geometric descriptors comes when you need to detect an image or a person or an image from a camera. So you need to train your camera to perform this particular functionality. So that's geometric descriptors. So in geometric descriptors, you have something called matching descriptors, which is distance. So distance is how far the object is from the camera. Or others will be like train index, index query, and image train index. So that deals with how you have a set of data, and how do you want to query, or how do you want to index that images to perform the calculation. And the other functionalities would be like tracking. Object tracking is something which is like essential when you're implementing camera. So like if you want to have a security module in there, you can just use this computer vision to like set up your own security system at home. Or fitting. So fitting is something like erosion and dilation. So let's say you have an image, and you want to add more pixels to this particular image to enhance this image. That is called dilating. And if you want to remove pixels from the image to like get a more constrained image, so that is called erosion of the particular image. So these functionalities can be used with OpenCV. And the other one would be camera calibration. So whenever you want to set up your camera, or let's say the computer camera or an ARM processor with a camera in it, so all these functionality starts with the configuration of your camera. So how do you configure the camera? That would be based on distortion matrix, a camera matrix, and a reprojection error. So all this data for configuring your particular camera can be exported into an XML or YAML to to have a configuration file of your camera. So even that you can do it through OpenCV. The only thing you need to concern is like when you're generating a YAML file, you just need another package installed in Python called YAML, and that would help you with generating the YAML file. Okay, so when you see these two images, what do you see, or what do you perceive? So if you want to detect changes in this image, or if you want to understand better of this image, or how do you perceive a static image, is what computer vision is all about. So let's see some of the enhancements that you can do based on an based on an image that you have, and some of the functionalities that computer CV, OpenCV will help you achieve. Deconvolution. So as soon as you talk about images, the first problem that you need to solve would be motion blur. So in a real-time data or real-time images that you get, most of the data would have a motion blur or any kind of blur in it. So how do you handle these blurs is what deconvolution is all about. So if you see these two images here, so you can somewhat vaguely understand that that is Las Vegas, but other than that, you have no credibility of getting like what the underlying text is. And if you see the second image, you can see a biker going in a bike, but you can't have more information relating to the helmet of the biker or relating to the handlebar of the biker. So once you implement deconvolution, this image will be enhanced, or like I said earlier, this image will be dilated to get your resultant set, which is more enhanced than what it actually is. So that is deconvolution. So this deconvolution is one of the functionality that we have in OpenCV. So in the deconvoluted image, you can clearly see that the top layer says welcome, and the second would say too fabulous, Las Vegas, Nevada. So this is the deconvoluted image of the previous image. If you can see the clarity of the previous image, I'll scroll it back. And even here in the second image, you can see the facial structure of the biker, and you can also see to an extent the handlebar of the particular bike. So you, based on this particular process of deconvolution, you get an enhanced image of a motion blurred source. So if you see here again, so just focus on the Las Vegas. So if you see that that's the blurred part of the image, and if you see here, this would be the deconvoluted image. Moving on, something called bounding boxes. So when you talk about face detection, so you implement an algorithm to detect faces. The first challenge what you face once the algorithm works is repetition of the boxes. It's called like overlapping bounding boxes. And the other one is called spurious response. So the top one is called multiple response, and the one which detects the hand is called spurious response. So as soon as you see this result, it means that your algorithm works fine. But you need to suppress those multiple responses and spurious response. So that can be done through something called non-maximum suppression. So that is an idea of reducing or suppressing the spurious response. So that is the spurious response, and that will be suppressed, and the multiple responses will be reduced to get the maximum, like the response out of it. So that can also be performed using OpenCV framework. So if you see here, the spurious response has been removed from the image, and the multiple responses has been reduced to the most accurate or the maximum response that we need from the picture. So that is also another functionality of OpenCV. So moving on for a demo. So this is a process to detect Parkinson's disease. So I believe that most of you would know what Parkinson's disease is. So for Parkinson's disease, how do you use or implement an AI approach to detect if the patient has Parkinson's disease or not, is what this demo is all about. The golden circle. So the golden circle is nothing but what, how, and why. So for this particular approach, what is the problem? The problem is detect Parkinson's disease based on geometric shapes. So Parkinson's disease is something that affects the central nervous system that would make the patient, he will face like tremors in his muscles or tremors in his motor functions. So based on that, in the year 2017, there was a study which stated that if you ask a patient to draw simple geometric shapes based on the pressure that's applied on the paper and the outlying geometrical shape, we can detect the early onset of Parkinson's disease. So from this research is what we try to implement like an AI model to detect if the person facing tremors in his muscles will have the same tremors applied on the diagram as well. So can you detect that tremor in the diagram based on an AI model? So that is this demo is all about. Okay, so this is a study. So it has been conducted by Zham et al. And he concluded that in order to detect Parkinson's, you can ask the person to draw a spiral. So you provide the outline of the spiral and ask them to follow the particular dotted lines to detect the tremors in the diagram. So this requires the speed of the pen movement and the pressure to analyze if the person has Parkinson's or not. So that is a study done in 2017. So for this, I have taken a data set from Center for Innovation and Technology Assessment in Health. So it's called NIATS. It's from an university in Brazil. And so we use an image data set of 204 images, and 104 images are of waves that you will see later, and the 102 images will be of the curves that we saw earlier. So we are dividing the data set into testing and training phase with 30 images for testing and 70 images for each for training. And so as you can see, you can get the data from the website provided to them. If you need some time, like taking a look at the URL, so that's the URL. So it's from a center called NIATS, NIATS. So it's from a University of Brazil. Yeah, so this is the data set which we have. So you can see the healthy patients and the Parkinson's affected patients. So if you ask them to draw a spiral and if you ask them to draw a wave, so this is how the healthy and Parkinson's patient would draw a wave. So this is just a sample set, and the whole data will have this kinds of data in it, the data set. And this data set is like pre-modified data set with training and testing data in it, and the label of the data, which we'll talk the reason why. So the data is labeled with 0 if the person doesn't have Parkinson's, and with 1 if the person has Parkinson's. And so, as I said earlier, so this is derived from University of Uberlandia from Brazil, and we are going to implement Python and OpenCV to detect if the person has Parkinson's or not. So the environment to work on this particular problem should include the following packages. So the first being OpenCV, and you can use the following code to import the OpenCV package in Python. So I would recommend going with Anaconda and then using the following commands so that it will be easier for you to use these packages. And so I did it in a Windows environment, like you can use Windows or Linux or any like Solar or any other platform that you need. So that would require the same packages as well. So and the next one would be scikit-image and scikit-learn. So in order to perform scientific calculations, that we'll be seeing like what it is and how we are implementing these packages into it. And the other one would be NumPy to perform the metrics calculation, and the other one would be IMutils, which is nothing but image utilities that you can use to work on the image. So we'll talk in depth like how we are using each of the packages in the upcoming model. So implementation of the detection script. So this following script would detect if the person has Parkinson or not. How do you implement this particular script is what we are going to see in front. So these are the packages that we are going to import for this. So the first one being we are using a random forest classifier. So the question might arise, like you have a problem and you need to solve. So the first step of solving the problem is which model you are going to use. So I can use deep learning here, I can use machine learning here, I can use simple data science concept here. So what am I going to use for this particular model? So this derives from the data set we have. So we do not have much data to work with. We only have like 204 images in total to work with, and when we split it, we just have 102 images to work with. So for this particular data, I cannot implement a deep learning approach, which requires several layering, and it also requires several features. So that would minimum it should have like an abundant data to train the model to provide particular results. So for this approach, we are going to go with random forest classifier. And like I said earlier, we have labels, so and we are encoding that label into an integer. So since the label already has the actual result in it, so whether it has Parkinson's or not, we are going to encode it into a label encoder. And then we are using montage. So montage is a concept where you provide a set of images as tiles. So like you saw in the image earlier for the data set, it had various sample sets as a tile, and then it would display if the tile has Parkinson's or not. So that is something called montage. I suggest you take a further look into how to implement montage. You'll see how we are implementing it, but if you can take more look into it, that would be great. And then we are importing a feature import. So this provides us something called histogram of oriented gradients. So everything we are dealing with is image. So how do you fetch the features from an image? So in this particular problem, we are going to use HOG, which is nothing but histogram of oriented gradients, to fetch the features of the image. So what are all the features of the image? The color of the image, or the size of the image, or to derive the shape in the image, because if you see in a spiral, if you draw, you need to detect those shakes. So how do you detect those shakes? So you can detect those shakes from the histogram of the particular image. So then we use NumPy. So NumPy, we are using NumPy for random indices and statistics calculation. So random indice is nothing but in the end, you select a random image for generating this montage, and then fetch the result of this particular image and display it as an output set. So for that we use random indices. And then for statistic calculation, it's nothing but in order to calculate the metrics of this particular model, let's say the accuracy, the specificity, the sensitivity of the particular model, we use NumPy as well. And then command line arguments. So in this approach which I tried, so that is using in command line, and then that would generate me, that would start working the model. So that's why we are using argparse. And the rest of the process is CV2 and OS. So CV2 is, so I've used version 2 of the computer vision, and then I'm using OS because, so I'm running in a Windows environment, so I need OS import to, pass on the Windows path. Yeah, so like I said, OpenCV2 would help me processing the images, and OS would give me Windows back. So quantification of the wave or quantification of the spiral. So what do you do to quantify this particular image that you already have? So that is nothing but feature extraction from the image, or like making this image into a more understandable format is what we're going to talk about now. So in this particular function, you implement something called HOG, which is, like I said, histogram of oriented gradients, and this would capture and quantify the local gradient in the input image. So if you see in the image, the features that I'm doing, I'm extracting the orientation and the pixels per cell, and then the cells per block. So this is something that I need to, like extract the features of that particular image. And so this would give me nothing but, for the spirals and the wave, it would help me detect if there is a shake in the image, so that I can say, okay, based on the shake and based on the thickness of the image, I can say, okay, this particular image is Parkinson affected image. Load and extract. So the first step of the model building would be to load the data set and then extract the particular model. So in this function, we are a function called load split. We will feed in the path to the data set, and then based on the path, we will perform the following set of functions to get a final output in a NumPy array. So the next step would be to once I feed in the image path, I would use the IMUtils functionality to extract the images path. So then what I would do is I would move forward to create two variables, which would be data, and the other one would be the labels. So the data will have the images, and the labels will have the label for the particular image. Like I said earlier, labels will already have the information whether it's affected by Parkinson's or not. So then what I would do is I would append this feature and label data, and then I would return it as a NumPy array. So if you see at the bottom, I'm returning it as a NumPy array after extracting the features. So what I'm doing in between is nothing but for each of the image in the path, I would extract the color and I would turn it into a black and white image. So when you're dealing with images, it is better if you treat it as a black and white image rather than colored image, because as soon as the image is colored, there are so many features that you have to work with to detect the color of the image. But here, if you're converting it to black and white, then the number of features you need to work with is less, but it's going to give you the same output as well. Then I'm converting it to a 200 by 200 pixel range, so that all the images are of the same size, and in the end we also have an image of the same color. So the next step would be threshold. So this is what we saw earlier. So thresholding is nothing but, so here what I'm trying to draw is I'm trying to convert this image which has white background and a black line into an image with black background and a white line in order to detect the line better. So if you have a white line, it is easier to detect the image. So this is a geometric shape, right? So in order to detect it better, I'm trying to put in a threshold value so that I can detect the image, or I can detect the lines better. And then by the end of this, I would have this entire data set as an image with black background and a white line and of a size 200 by 200. And I would just append it to a NumPy array that would have data and labels separated. Command line arguments. So this is where I'm passing in the source of the data, and if you see here, the first command line argument would be I would pass in the data set. So, and the second step would be I would pass in the number of trials it should run to build the model. So how many times do you want to rerun this model so that you get a specific output that you need. So for here, I'm going to default it to 5, but you can set it more than 5 to get more number of trials to run the particular model. So that is what it is. Training preparation. So once you have the source set brought in, what you need to do is you need to train this model. So before you go forward with training the model, so you have so what you have right now in hand is nothing but a complete set of data with images that has been transformed, and then it has been made to a machine readable format. So this is the step that you need to do before training the model. So once you have this done, you need to go. You can go forward into training your model. So that would be the first step. Would be to you need to split the data into testing and training. So that is the basic step that you do for any data science or a AI or a machine learning part. So you divide the data set into training set and the testing set to perform training and testing. And the second step would be to perform you have a trials dictionary, and then we have defaulted by 5. So you initialize the trials dictionary and then perform training. So if you see here, we are passing the data set into the load split method that handles the changing of data. So when you pass the image, so you are passing it like a raw image, and then you are passing it to the load split, and this load split will turn it into a machine readable format. And the label encoder will encode the label of the particular image, and then we'll initialize the trial dictionary to how many times do you want to run the trial based on the defaulted value. So starting the trials. So in this particular range, what we are going to do is like for first we will initialize the random forest model, and then you try to make predictions on the testing data. So if you see here, we have a range for the trial. So for each of the trial range, so here it is 5. You try to implement the random forest model, and then you try to fit in the training data. So once you fit in the training data, the model will start executing, and then you, by the end of the model.fit, you will have a working model in your hand. So and then you pass in the testing data to get a prediction. So you have the predicted image from the model, you feed in the data and you get a prediction out of the model. So how do you determine, okay, so this is a good result or this is a bad result? How do you determine that? So you determine that based on metrics. For this metrics, we can use NumPy, and that's what we saw. So for this, we are going to make use of 3 of the metrics. One would be accuracy, so how accurate the model is, and the other one would be sensitivity, how sensitive the model is. I'm going to talk about sensitivity and specificity later. So so that is sensitivity and that is specificity. And then what you're going to do is like you're going to update the trials dictionary with whatever you had. So and then you would feed in the metrics as well to get the final metric of the image to get the performance of the particular model. So then we have the next step should be to print the statistical information of the particular model. So like I said, you need to print out the sensitivity, accuracy, specificity of the model. So how do you do it? So for this, you're going to use a NumPy framework to, first for each of the values in the metric, you would determine mean of the value to get the accurate, for let's say accuracy, you determine the mean of the accuracy values to get the average accuracy of the particular model. And let's say if it's specificity, you provide a mean for all the values to get the average specificity of the particular model. And then we have standard deviation. So you provide, if in order to get a standard deviation of that particular model, you use the standard deviation using NumPy. And so this is nothing but to get the statistics of the model. So how good your model is, or like how much do it need to improve so that you have a better model in your hands. So yeah, like I said, we loop over each of the metrics and then we grab the values based on the mean or standard deviation. And then we'll display it in the terminal. Creating a montage. So this step would be to get the final end result that you need in the model. So montage is nothing but first we will read the path, and then we'll select a sample in random from the test set, and then we would copy the particular image. So after we do this copy from the test set, you need to transform this image into like what we did earlier in the model. Like you need to change the color, you need to change the histogram, and then you need to resize the image to like 200 by 200. So that's what we're doing. First we are resizing it to 200 by 200, and then we are setting a threshold where it is converted into like black background with a white line. And then we are, before that we are also converting it into a black and white image. So that's what this part of the code is all about. So yeah, so we randomly sample the image from our testing set, and then we using open. So what we are going to do is like once you generate the montage of the images, you have a 5x5 tile with the diagrams in it, and then you're going to use OpenCV to add text to the leftmost corner of the image, indicating that it is okay. So this is affected by Parkinson's or not. So that's what we're going to do in the upcoming step. So classification of image. So you have a montage of images, and then for each of the image, you're feeding the image into the model, and you're getting the output. And based on the output, you're going to classify this montage into a result set with detection of the Parkinson's or not. So if you see here, you have the features quantified. So that is nothing but getting the histogram of gradients, and then you're feeding in that feature. So what you're feeding in is basically not the image itself, but the data which we collected from the image. So we saw earlier that from the image we extract the features using the HOG, and by the end of that feature extraction, you're passing the feature to the model and you're getting the output. So then what we do is, like, based on that, we are creating a new window. So if you're using Windows, you need to use these two steps, like CV2 start window and CV2 named window, to generate a new window in Windows. But in Linux environment, it should be fine that you are using it or not. We can ignore this two statements, and then by the end you would have, if it's healthy, you would get an image with green stating that it's healthy. If it's not, you would get an image stating that it's affected by Parkinson's in red. So yeah, so this is the whole model is about. So let's see the output of how it works. So for our spiral model, we have the following results. So when you execute the code, you would get a result set such as this. So here, the accuracy and sensitivity and specificity. So we are going to discuss like what accuracy and sensitivity and specificity is. So yeah, so this is the output. So if you see here, in the first row, first image, you can still see tremors, but the model has said that it is a healthy image. And in the fourth row, first image, you don't see a lot of tremors, but still the model has detected that it has Parkinson's. So the first image is called false positive, and the second image is called true negatives. So as far as medical imaging is concerned, false positives are fine. So if a person doesn't have Parkinson's and the image and the model says, okay, he has Parkinson's, that is fine, because again the doctor is going to provide his diagnostic as well, stating that, okay, you don't have Parkinson's, using other tests. But true negatives are of a problem, because like if the person has Parkinson's and the model says, okay, you don't have Parkinson's, that's a problem, because like he has Parkinson's, and that should be minimized as possible. So that is what sensitivity and specificity is all about. So in specificity, you detect the true negatives, and in sensitivity, you detect false positive. So, but you have to make sure that this is like an increase in the threshold, where it is increased to a point where the actual Parkinson's should not be detected as you don't have Parkinson's, and actual healthy should not be detected as you have Parkinson's. So how you balance that is how you improve the sensitivity and specificity. And then you have the results for the wave model. So this will be the result for the wave model, and then this is the window that you get. So this is the montage that I was talking about. And for that, I'll show you the demo. So this is the code that we have. So I'm copy pasting this result set, the data set. Executing this data set would give me the image. So if you see here, this is what you get as an output. And these are the resources that helped me preparing for this presentation. So the first one would be the OpenCV library. And so this is an open source library. So if you are interested in it, you can even contribute to this library and make it better and bigger. And then comes PyImageSearch. So PyImageSearch by Adrian Grossbrock is a wonderful resource for you if you want to start out with AI, deep learning, image detection, or motion detection, or applications in that category. And then we have other resources that help me, coming up with this. And this is me, Rakesh. So I'm an analyst at Jade Global, and I currently do my master's in software engineering. So the project that I just showed you is my capstone. So what I'm trying to do is so this is just for Parkinson's disease. I'm trying to implement the same approach for malaria and breast cancer as well. So I have a collection of images for malaria detected patients. So that is like an microscopic images. And then for breast cancer images, we have scans of the people with breast cancer and not. So that is a data set that I have acquired or from open source websites. So I'm trying to implement this particular approach to those problems as well. And thank you so much for having me out here, and you've been a very good audience for helping me explain what I'm doing. So thank you.
I could take like a couple questions and short questions.
Yeah.
Why inverting an image makes it easier to write a line?
So if you see since this image is drawn by a pencil or a pen, so in order to detect that line efficiently, if we convert it into a white line rather than being it in a colored line, since we are converting it to a grayscale image, right? So if we convert it into a white line, it's easier to detect for the HOG generation to extract the features from the image.
Is this something that you experiment with and find out?
So this is a well-known, like an approach when we are handling geometric shapes in the image.
Increasing the number of times this model gets
diodes?
trained,
Mm-hmm.
will it help in improving the true negative value and
It would help to an extent, but it won't be that much because as far as AI and machine learning is concerned, it's all about the amount of data you have. So if you are handling 204 images data, no matter how much trial you improve, it's not going to improve after a specific point.
But suppose in case you have
Huge data.
amount of data.
Yeah, so if you have huge data and if it's not this particular problem, if it's a different problem, then I would suggest going with deep learning approach where you have layers, and then that would give you a more detailed output rather than going with random forest.
Thank you all, and if you have any other questions, he can answer outside in the hallway.
Thank you so much.
Have a good day.
Sorry about that, Arj.